There is a question so vast, so quietly devastating in its implications, that most people who stumble upon it find themselves standing very still for a moment, as though the ground beneath them has become uncertain. It is a question that arrives not with the thunder of great philosophical disputes, but with the soft, relentless pressure of a tide coming in. You think you are standing safely on the shore of understanding, and then the water is around your ankles, and then your knees, and then you realize that the shore itself was never as solid as you believed. The question is this: if the Big Bang created the universe, if that single, incomprehensible eruption of energy in space-time gave birth to everything that has ever existed, every atom in your body, every star in every galaxy, every thought you have ever had, then what, in all the depth of possible existence, created the Big Bang? It seems, at first, like a simple question. A child asks it. A philosopher asks it. A physicist, staring at equations at 3 in the morning with cold coffee growing a skin beside the keyboard, asks it. And the remarkable thing, the thing that should stop us all in our tracks and remind us how young and how brave and how beautifully confused our species is that we do not yet know the answer. We have theories. We have mathematics of extraordinary elegance. We have machines buried under mountains and stretched across continents, listening and measuring and recording. We have minds of singular brilliance devoted entirely to this pursuit. And still, the question stands, patient as the cosmos itself, waiting. To understand why this question is so profound, we must first sit with what we mean when we say the Big Bang. We must resist the temptation to think of it as an explosion in any conventional sense, the kind you might see in a film, a great fireball expanding outward into pre-existing darkness. That image, however vivid, is misleading in almost every important way. The Big Bang was not an explosion inside space. It was an explosion of space itself. There was no pre-existing void into which the universe expanded. There was no place outside the universe waiting to receive it. Space and time themselves were born in that first instant. The Big Bang was not something that happened in the universe. The universe was something that happened in the Big Bang. This distinction is not merely semantic. It is the pivot around which everything else turns. When we ask what came before the Big Bang, we are already in territory where the question itself may be malformed. The word before implies time. It assumes that time stretches backward without limit, like a river that must have its source somewhere upstream. But if time itself began at the Big Bang, if there is no upstream, no before, no earlier, then asking what came before the Big Bang is like asking what is north of the North Pole. The question uses language correctly. It is grammatically sound. And yet it does not point to anything that can meaningfully exist. Stephen Hawking, whose mind moved through the landscape of theoretical physics the way a hawk moves through air, described this with characteristic clarity. He proposed that the boundary condition of the universe is that it has no boundary. In his no-boundary proposal, developed with physicist James Hartle, time near the very beginning of the universe behaves differently from the time we experience now. In our everyday existence, and even in the cosmic present, time is a direction. It moves, it flows, it carries causality along with it. But in the extreme conditions of the universe's birth, Hawking and Hartle suggested, time becomes more like space. It acquires an additional degree of freedom. And in this imaginary time, as Hawking called it, the universe has no singular beginning point, no moment of creation, no edge where something must have pushed it into existence. We must pause here, because imaginary time is one of those phrases that sound like poetry but is actually mathematics. In the formalism of quantum mechanics and general relativity, there is a technique in which time is treated as a complex number, rotated, in a sense, so that it takes on spatial character. This is not a metaphor. It is a mathematical tool that physicists use to perform certain calculations, a trick that sometimes reveals deep truths about the nature of things. When Hawking speaks of imaginary time, he is not suggesting that time is a dream or an illusion. He is pointing toward a possible description of reality in which the question of what came before becomes as empty as asking what is south of the South Pole when you are already at the southernmost point. And yet, for all its mathematical beauty, the Hartle-Hawking proposal is one answer among many. It is a hypothesis, not a settled fact. Science is not a collection of certainties handed down from authority. It is a process, a way of asking questions and testing answers, an ongoing negotiation between the human mind and the nature of reality. And the nature of reality, it turns out, is under no obligation to be simple, or comfortable, or comprehensible to creatures who evolved to find food on a savanna. Our brains are remarkable instruments, but they were not designed, by any process, to intuitively grasp the topology of space-time near a singularity. To go deeper into this question, we must confront the concept of a singularity itself. When physicists trace the history of the universe backward, when they run their equations in reverse, watching galaxies converge, matter condense, temperature rise, space contract, they arrive at a point where the equations break down. The density becomes infinite. The curvature of space-time becomes infinite. The temperature becomes infinite. And when a physical quantity becomes infinite in an equation, it is usually a sign not that infinity actually exists in nature, but that the theory being used has reached the edge of its validity, that something new and as yet unknown must take over. The singularity at the beginning of the universe is almost certainly not a real physical object. It is a sign, written in the language of mathematics, that our current understanding is incomplete. This incompleteness is not a failure. It is an invitation. It is the universe whispering, in the only language it knows, that there is more to discover. General relativity, Einstein's magnificent theory of gravity, of space-time curvature, of the large-scale structure of the cosmos, breaks down at the singularity. Quantum mechanics, the equally magnificent theory of the very small, of probability waves and uncertainty and the discrete nature of energy, also breaks down at the singularity, or rather, it has not yet been properly reconciled with general relativity in a way that would allow it to describe such extreme conditions. What we need, and what we do not yet fully possess, is a theory of quantum gravity, a framework that unifies the very large and the very small, that describes space-time itself as a quantum object, subject to the strange laws of uncertainty and superposition that govern electrons and photons and the foundations of matter. Several candidate theories exist. String theory is the most famous, perhaps the most ambitious, a framework in which the fundamental constituents of reality are not point particles but one-dimensional vibrating strings of energy, and in which extra dimensions of space, curled up at scales far too small for any current instrument to detect, give rise to all the forces and particles we observe. In string theory, there is no singularity at the Big Bang. The strings themselves, and the geometry they inhabit, prevent the infinite densities that appear in the classical equations. What happened at the very beginning is smeared out, in a sense, by the quantum nature of the strings, replaced by a finite but extraordinarily hot and dense state that physics can, in principle, describe. Then, there is loop quantum gravity, a different approach that takes space-time itself and quantizes it, makes it granular, discrete, built from fundamental units of space and time at the Planck scale, that almost incomprehensibly small length of approximately 10 to the power of -35 meters where quantum effects become dominant. In loop quantum gravity, Space is not continuous, like a smooth fabric, but pixelated, made of discrete loops and networks. And in this framework, the Big Bang is replaced by what some theorists call the Big Bounce. The universe did not begin from nothing. It contracted, a previous universe collapsing inward under its own gravity until it reached a minimum size set by the quantum of space, and then rebounded, expanding outward into the universe we inhabit today. The Big Bounce is a remarkable idea. It is the universe breathing, inhaling, holding for an eternity measured in the Planck time, and then exhaling in a great cosmic breath that we experience as the expansion of everything. In this picture, the question of what came before the Big Bang has an answer, and the answer is another universe. A predecessor cosmos, governed by the same laws, or perhaps by slightly different ones, which collapsed and gave birth to ours. And if one asks what came before the universe, the answer spirals backward to an infinite regress of bouncing universes, each arising from the collapse of its predecessor, none of them having a true beginning, none of them having a true end. There is something deeply satisfying about this picture, aesthetically and philosophically. It is a vision of the cosmos as fundamentally cyclical, echoing the intuitions of many ancient traditions, the Hindu concept of the kalpa, the great cosmic cycle of creation and dissolution, the Stoic ekpyrosis, the conflagration of the world followed by its rebirth, the universe as an eternal process rather than a finite event. But we must be careful not to confuse aesthetic satisfaction with physical truth. Nature, as we have learned again and again, does not arrange itself to please our sense of beauty or our desire for symmetry. It arranges itself according to principles that we are still learning to read. And so the Big Bounce remains a hypothesis, a beautiful and mathematically interesting one, but not yet confirmed by observation. The signature of a previous contracting universe might, in principle, be encoded in the cosmic microwave background radiation, that faint glow of ancient light that fills the universe in every direction, the afterglow of the hot, dense early cosmos, released when the universe was approximately 380,000 years old. Some physicists have searched the cosmic microwave background for patterns, for circles or other anomalies that might represent the imprint of a previous aeon. The results have been suggestive in moments, but not yet conclusive. The cosmos keeps its secrets with magnificent patience. We must now speak of another class of answers to our great question, answers that go by the name of eternal inflation. To understand eternal inflation, we must first understand ordinary inflation, which is itself one of the most extraordinary ideas in modern cosmology. In the early 1980s, physicist Alan Guth was working through the implications of some particle physics theories on the early universe and realized something remarkable. In the very first fractions of a second after the Big Bang, in an interval so brief it makes the word brief seem like an overstatement, roughly 10 to the power of negative 36 seconds, the universe may have undergone a period of exponential expansion, growing in size by a factor of at least 10 to the power of 26, possibly far more, in an almost instantaneous moment. This inflation, driven by a hypothetical field called the inflaton field temporarily in a high-energy false vacuum state, would explain several features of the universe that otherwise seem impossibly fine-tuned. It would explain why the cosmic microwave background is so extraordinarily uniform in temperature across regions of the sky that, without inflation, could never have been in contact with each other. They would have been causally disconnected, unable to exchange energy or information, and yet they arrived at the same temperature to better than 1 part in 10,000. Inflation solves this by saying that all those regions were once in contact, close together, before inflation stretched the universe to its current vast scale. Inflation also explains why the universe appears geometrically flat, why it does not curve back on itself or curve away from itself at detectable scales, why the total energy density of the cosmos sits so precisely at the critical value. And it explains the origin of the large-scale structure we observe, the galaxies and clusters and superclusters and cosmic filaments, by stretching quantum fluctuations in the inflating field to macroscopic scales, seeing the density variations that gravity later amplified into the cosmic what we see today. But here is the remarkable extension. When physicists explored the mathematics of inflation in more detail, they found that inflation, once started, is extraordinarily difficult to stop everywhere at once. In most regions of an inflating universe, the inflating field reaches the bottom of its potential and inflation ends, giving rise to a hot, dense universe like ours. But quantum fluctuations ensure that in some regions, the inflating field is briefly kicked back up to its high energy state. In those regions, inflation continues and continues exponentially. The inflationary patch grows faster than inflation can end within it. New regions are constantly being created by inflation, even as other regions exit inflation and become universes like ours. This is eternal inflation. Once it begins, it never ends globally. The universe as a whole, the multiverse, is a perpetually inflating sea, from which bubble universes like ours constantly nucleate and expand, each one representing a region where inflation has ended and a hot Big Bang has occurred. In this picture, our Big Bang was not the beginning of everything. It was the local end of inflation in our particular bubble, a phase transition in a larger inflating background, a moment when the inflating field in our region finally settled into its low energy state and released its energy as the heat and radiation of our early universe. The eternal inflation picture is staggering in its implications. It suggests that our universe is one of an inconceivably large number of bubble universes, perhaps an infinite number, each one potentially with different physical constants, different laws of nature, different possibilities for the emergence of complexity and life. In some bubbles, the force of gravity might be slightly stronger, causing them to collapse before stars can form. In others, the electromagnetic force might be different, making chemistry impossible. In ours, the constants are what they are, and here we stand, contemplating the whole. There is a version of this picture that connects to string theory in a particularly elegant way. String theory, it turns out, does not predict a unique universe. It predicts an enormous landscape of possible universes. Estimates range from 10 to the power of 500 to much larger numbers, each corresponding to a different way the extra dimensions of string theory can be compactified, curled up at small scales. Each configuration produces different effective laws of physics in the large three-dimensional space we experience. By itself, this landscape seems like a failing of string theory, an embarrassment of riches that prevents any specific prediction. But combined with eternal inflation, it becomes something else entirely. If eternal inflation is constantly creating new bubble universes, and if string theory provides an enormous landscape of possible physical configurations, then eternal inflation might explore the entire landscape over cosmic time, randomly assigning physical constants to each new bubble as it nucleates. Our universe would be one particular patch in this vast exploration, one specific configuration among the nearly infinite possibilities, and we would find ourselves here not because these constants were designed for us, but because only in configurations like ours can stars form, planets form, chemistry happen, life arise, and minds emerge to ask questions about the whole. This is the anthropic principle in its most powerful form, not a design argument, but a selection effect. We are, in a sense, survivors of the multiverse lottery. We do not observe the universes with wrong constants because in those universes, there is no one to observe. The very fact of our existence selects for a universe capable of producing beings who can observe it. This is a profound and somewhat unsettling thought, because it suggests that certain properties of our universe may not have deep causal explanations. They may simply be the values that our particular bubble happened to receive from the random quantum processes of the inflating sea. The cosmological constant, the energy density of empty space, the mysterious dark energy driving the accelerating expansion of the universe, may be the value it is not because some deep principle required it, but because in bubbles where it is much larger, galaxies never form, and in bubbles where it is much smaller or negative, the universe collapses. We live in one of the habitable bubbles. But we are getting ahead of ourselves, in the way that minds exploring the edges of knowledge always do, pulled forward by the gravity of the questions. Let us step back and consider another possibility, one that does not invoke inflation or bouncing or multiverses, but asks an even more fundamental question. Why is there something rather than nothing? This question, articulated most famously by the philosopher Gottfried Wilhelm Leibniz in the 17th century, is perhaps the deepest question of all. Even if we could fully explain the Big Bang, even if we had a complete theory of quantum gravity that described the universe's emergence from a quantum state with perfect mathematical precision, we would still face this deeper puzzle. Why does anything exist at all? Why is there a universe governed by physical laws rather than pure emptiness? Why are there laws at all? The physicist Lawrence Krauss wrote a provocative book arguing that the universe could arise from nothing, from the quantum vacuum, spontaneously, to the well-understood processes of quantum field theory in which particles and antiparticles constantly pop into and out of existence. But Krauss's nothing is not the philosopher's nothing. His nothing is the quantum vacuum, a seething, dynamic, mathematically rich structure governed by physical laws. The philosopher's nothing is truly nothing. No space, no time, no laws, no mathematical structures, no possibility of anything. And the gap between those two nothings is, perhaps, the largest gap in all of human knowledge. The physicist Alexander Vilenkin proposed a specific mechanism by which the universe might have tunneled into existence from nothing, using the mathematics of quantum tunneling, the well-established quantum phenomenon by which particles pass through energy barriers that classical physics says they cannot cross. The Lincoln universe tunneled from a state of no space, no time, no matter, no energy, into a small, closed de Sitter space, and then inflated. The probability of this tunneling event is not zero in his calculation. And in an infinite void of nothing, any event with non-zero probability will eventually occur, given infinite time, but there is no time in nothing, or given, perhaps more precisely, that the absence of time does not prohibit the quantum event from occurring, the universe simply appears. There is something almost mystical about this picture, and yet it is written in the dry, precise language of tensor calculus and quantum field theory. The universe tunneling from nothing is not a supernatural event in Vilenkin's framework. It is an extrapolation of well-tested quantum principles into a domain where no experiment has ever gone. It is a leap of mathematical faith, supported by the remarkable effectiveness of quantum mechanics in every domain where it has been tested, and by the reasonable hope that a theory that works so brilliantly everywhere we can observe might continue to work in regimes we cannot. But hope, however reasonable, is not the same as knowledge. Let us consider the role of time more carefully, because time is the hidden protagonist of this entire story. When we ask what came before the Big Bang, we are implicitly assuming that time is like space, that you can move through it in any direction, that there is a past and a future and a present that slides between them, and that this structure extends infinitely in both directions. But we have known since Einstein that time is not like this. Time is deeply entangled with space. Time is affected by gravity. Time runs at different rates in different gravitational fields, a fact so well established that GPS satellites must correct for it, or their navigation would drift by kilometers per day. Time, in general relativity, is not a backdrop against which the universe plays out. Time is part of the universe, a dimension of the four-dimensional space-time fabric that the universe is. And if time is part of the universe, then asking what happened before the universe is asking what happened before time. It is possible, not certain, but genuinely possible, that this question has no answer, not because we lack the intelligence or the instruments to find one, but because the question itself is structurally empty, like asking for the color of a sound or the weight of a Wednesday. Language gives us the grammar to construct the sentence, but reality does not supply the referent. The concept of before requires time. Before the universe, there may simply be no time, and therefore no before. But here we must be careful about another assumption, one that is so deeply embedded in human thinking that we rarely notice it. We assume that time is one-dimensional, that it is a line, or at most a branching tree, with one direction called future and another called past. But in the exotic mathematics of quantum gravity, this need not be so. Some theories suggest that near the Planck scale, time may be as fuzzy and uncertain as position and momentum are in ordinary quantum mechanics. There may not be a single, well-defined sequence of events. There may not be a unique history stretching back to a unique moment of creation. The universe's past may be, in some deep and technical sense, a superposition of many histories, each with its own amplitude, and what we experience as the definite history of our cosmos may be the result of a quantum decoherence process, a selection from among many possible paths by the act of our existing in this particular present. Richard Feynman's path integral formulation of quantum mechanics gives us a way to think about this. In Feynman's approach, a particle does not follow a single path from one point to another. It follows all possible paths simultaneously, with each path contributing a complex amplitude to the final probability. The most probable path, the classical trajectory, is the one where nearby paths interfere constructively. Applied to the universe as a whole, in the quantum cosmology program pioneered by Hawking, Hartle, and others, this means the universe is described by a wave function, the wave function of the universe, a mathematical object that encodes the probability of every possible configuration of space and matter and energy. The universe does not have a single history. It has a quantum superposition of all possible histories, weighted by their probabilities. In this framework, asking what created the Big Bang is like asking which specific path a photon took on its way through a double slit. The photon did not take a specific path. It took all paths, and the interference of those paths produced a pattern on the screen. The universe did not begin with a single specific event caused by a single specific prior event. It began, or rather, it is, a quantum object, described by a wave function that assigns probabilities to various histories of origin and development. Our particular history, the one we observe and inhabit and wonder about, is one realization of that wave function, perhaps the most probable one given our existence as observers within it. This is not mysticism. It is the most careful application of our best physical theories to the hardest problem we know. But it is also profoundly incomplete. The wave function of the universe requires boundary conditions, rules about what states are allowed at the beginning. Hartle and Hawking proposed the no-boundary condition, which we have already visited. The Lincoln proposed creation from nothing. Others have proposed different boundary conditions, each leading to different predictions about the large-scale properties of the universe we observe. and the question of which boundary condition, if any, is the correct one, is not yet settled. There is a school of thought that asks whether the laws of physics themselves require explanation. We have been assuming, throughout this conversation, that the universe arises from within a framework of physical laws, that the Big Bang happened because certain equations, the Einstein field equations, the Schrödinger equation, the standard model of particle physics, describe something real about nature and that nature follows them. But why do those particular equations describe reality? Why not different equations? Why does mathematics describe nature at all? This is what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics, the mysterious and deep fact that abstract mathematical structures developed by human minds, often without any practical motivation, turn out to describe physical reality with uncanny precision. The physicist Max Tegmark has taken this thought to its logical extreme in what he calls the mathematical universe hypothesis. If mathematics describes physical reality so well, he asks, perhaps this is because physical reality is mathematical structure. Not that mathematics is a tool we use to describe the universe, but that the universe is a mathematical object, literally, not metaphorically. In Tegmark's view, all mathematically consistent structures exist physically. Our universe is one such structure, and the apparent fine-tuning of its constants is explained, as in the multiverse picture, by the fact that we can only find ourselves in structures capable of supporting our existence. If Tegmark is right, then asking what created the Big Bang is asking what created a particular mathematical structure. And the answer, in his framework, is that mathematical structures do not need to be created. They simply are. They exist in a realm of pure mathematical necessity, timeless and causeless, just as the number 7 does not need to be created and does not exist in time. Our universe's existence is no more mysterious, and no less wondrous, than the existence of the integers. This is either a profound illumination or a category error of cosmic proportions, perhaps both. We have been circling around a certain possibility without quite facing it directly. The possibility that the universe has no cause, that it simply exists, without antecedent, without explanation, without reason. This is philosophically unsatisfying to most human minds, because our minds evolved to find causes, to trace chains of causation, to ask why and to expect an answer. The universe as an uncaused fact is deeply uncomfortable. And yet, in logic, every chain of explanation must end somewhere. If we say God created the universe, we must ask what created God. If we say a parent universe created our universe, we must ask what created the parent universe. If we say mathematical structures exist timelessly, we must ask why there are mathematical structures rather than nothing. At some level, the explanatory chain must terminate in something that simply is, without further explanation. Perhaps the most honest thing we can say is that the universe is that terminal fact. Perhaps the universe is the thing that has no prior cause, the foundation upon which all other explanations rest. This is not intellectually satisfying. But intellectual satisfaction is not a reliable guide to truth. The universe does not owe us a story that feels complete. It offers us what it is, and our task is to understand it as best we can with the instruments and intelligence we have been given by the very processes we are trying to understand. There is something humbling and exhilarating in this situation. We are creatures of the Big Bang, assembled from elements forged in stellar furnaces, giving consciousness by 4 billion years of biological evolution, peering back through time with our telescopes and our mathematics, trying to understand where all of this came from. The atoms in our brains, the carbon, the oxygen, the nitrogen, the hydrogen, were present in the early universe, scattered through the cosmos in the first minutes after the Big Bang, drawn together over billions of years by gravity, cooked in stars, scattered by supernovae, gathered into planets, organized by chemistry and biology into nervous systems capable of self-reflection. We are the universe's way of asking about itself. We are the question and, perhaps someday, part of the answer. Consider for a moment the cosmic microwave background radiation, that faint glow at a temperature of 2.725 degrees above absolute zero that permeates all of space. This radiation is a photograph of the universe at 380,000 years of age, the oldest light we can directly observe, the surface beyond which the universe is opaque to photons. In this radiation, the Planck satellite and its predecessors have found tiny temperature fluctuations, variations of 1 part in 100,000, that encode the seeds of all the structure in the universe. Those fluctuations, we believe, were seeded by quantum processes during inflation, stretched to cosmological scales by the exponential expansion of the inflaton field. In the patterns of the cosmic microwave background, we are reading the quantum signature of the universe's birth. We are decoding, in the oldest light available to us, the fingerprints of processes that occurred at energies far beyond anything our particle accelerators can reach. And buried in that ancient light may be information about what came before. If the universe bounced from a previous contracting phase, there might be faint signatures, specific patterns, specific deviations from perfect Gaussian statistics, imprinted in the microwave background by the contracting phase before the bounce. If eternal inflation occurred, gravitational waves produced during inflation should have left a specific pattern of polarization in the microwave background, a swirling pattern called B-modes, whose amplitude would tell us the energy scale of inflation and constrain the models. Several experiments have searched for these primordial B-modes. The BISET-2 experiment in 2014 announced their detection, a moment of tremendous excitement that turned out to be premature. The signal was contaminated by dust in the Milky Way. The search continues with new and more sensitive instruments because it detected primordial gravitational waves would be the most direct window yet into the physics of the universe's very first moments. We should also speak of the second law of thermodynamics, which is perhaps the most fundamental and least escapable law in all of physics. The second law says that entropy, the disorder, the number of possible arrangements of a system, tends to increase over time. Broken eggs do not spontaneously reassemble. Heat flows from hot bodies to cold bodies, never spontaneously in reverse. The arrow of time, the difference between past and future, the reason memories work in one direction and not the other, is fundamentally rooted in the second law. The past is remembered because it has lower entropy. The future is uncertain because entropy can only increase. Now here is a deep puzzle. The universe today is far from its maximum entropy state. There are stars burning with ordered nuclear energy, living organisms with extraordinarily low internal entropy, galaxies with structured spirals and bars and halos. All of this order exists because the early universe had very low entropy, because the Big Bang produced a universe in a state of remarkable, almost inexplicable order. If entropy must increase, then the early universe must have been in a very special, very low entropy state. And asking what created the Big Bang is, from a thermodynamic perspective, asking where that extraordinarily low entropy initial condition came from. The physicist Roger Penrose has spent decades thinking about this question and arrived at a striking answer in his conformal cyclic cosmology. Penrose proposes that our universe is one aeon in a sequence of eons, each aeon being a universe that begins in a hot, dense, low entropy state, expands for trillions upon trillions of years, and ends in a cold, dark, maximally entropic state dominated by black holes, which eventually evaporate away through Hawking radiation, leaving only photons, and a few massless particles and a universe with no meaningful scale. Here is the crucial insight. In such a universe, without mass, conformal symmetry is restored. The laws of physics become scale invariant, and what looks like a maximally expanded cold infinite universe becomes, to a conformal transformation, mathematically equivalent to a new hot, dense Big Bang. The end of one aeon is the beginning of the next. The universe reindents itself, not through a bounce, but through a mathematical equivalence, an identity between extreme ends of the cosmic life cycle. Penrose's conformal cyclic cosmology makes specific predictions that are potentially testable. The black holes of the previous aeon should leave traces in our cosmic microwave background. Concentric rings of slightly different temperature variance, halos centered on the locations of major black hole mergers in the previous universe. Some researchers have reported finding such rings in the data. The statistical significance is debated. The history of cosmological data analysis is full of patterns that turn out to be noise, and also full of patterns that turn out to be real. We must hold these results with appropriate uncertainty, neither dismissing them nor celebrating them prematurely. Let us now take a step even further back and ask a question that physics has not traditionally considered its territory, but which may ultimately be unavoidable. Not just what came before the Big Bang, but why the universe is intelligible at all. Why does it follow laws? Why does it not behave randomly, chaotically, without pattern? The fact that the universe is mathematically describable, that it follows equations, that the same physical laws hold in distant galaxies billions of light years away, and billions of years in the past as they hold here and now in this moment. This lawfulness of nature is not something we can take for granted without explanation. Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. He was not speaking mystically. He was pointing to something genuinely puzzling. The universe did not have to be this way. A universe of pure chaos, where anything could happen at any moment without rhyme or reason, is logically possible. And yet, we find ourselves in a universe where hydrogen atoms on the far side of the observable cosmos have the same spectral lines as hydrogen atoms in our laboratory, where the speed of light is the same everywhere and always, where the same equations that govern the motion of billiard balls on a table, suitably extended and modified, also govern the orbital mechanics of binary pulsars 1,000 light-years away. This universality, this lawfulness, is one of the deepest mysteries of existence. Some physicists and philosophers argue that the laws of physics are themselves necessities, that they could not be otherwise, that any consistent mathematical universe must have something like the laws we observe. This view, sometimes called physical necessity, holds that the equations of nature are not arbitrary choices, but logical consequences of coherent existence. Others argue that the laws are contingent, that they happen to be this way, that other laws are genuinely possible, and that the question of why these laws hold is as legitimate and as open as the question of why there is something rather than nothing. The anthropic principle, in various forms, has been invoked to address this. If the laws were different, we would not be here to observe them. Our existence selects for law-governed universes with constants in the right range. But the anthropic principle, while logically valid, is not fully satisfying as an explanation. It tells us why we observe what we observe, but it does not tell us why there is a large collection of universes with different laws to select from. It pushes the question back one level. Why is there a multiverse? Why is there anything for selection to operate on? We are, at this point, approaching the edge of what physics can say, and entering a borderland where physics, philosophy, and perhaps something else entirely must collaborate. The question of what created the Big Bang is, at its deepest level, not purely a scientific question. It is a question about the nature of existence itself, about why there is something rather than nothing, about whether existence requires cause or whether it simply is. Science can tell us an enormous amount about how the universe began, about the physical processes of the early moments, about the nature of inflation and quantum fluctuations, and the hot dense plasma of the first seconds. But the ultimate why, the reason there is a universe at all rather than absolute nothingness, may be beyond the reach of any physical theory, not because science is limited in principle, but because the question itself may not be the kind of question that has a physical answer. There is a tradition in physics that holds that the ultimate theory of everything, when and if we find it, will be unique, that there will be only one consistent, mathematically complete description of all of physical reality, and that this uniqueness will itself explain why the universe is as it is. John Archibald Wheeler, one of the most creative and provocative minds in 20th century physics, dreamed of a law without law, a universe that bootstraps itself into existence, where the laws of physics are not given from outside but emerge from the structure of the universe itself, where the universe participates in its own creation through the act of observation, in the language of quantum mechanics. Wheeler's vision was influenced by his deep engagement with quantum mechanics, particularly with the measurement problem, the puzzle of how the quantum superposition of possibilities collapses into a single definite reality when observed. In standard quantum mechanics, observation plays a fundamental role. The act of measurement selects one outcome from many possible ones. Wheeler extended this, provocatively and perhaps too boldly, to cosmology. In his participatory universe, observers are not passive recipients of a pre-existing reality. They are participants in bringing reality into being. The universe, in Wheeler's poetic formulation, is a self-excited circuit, a cosmic loop in which the universe gives rise to observers and observers give rise to the universe. This idea is controversial among physicists, for good reason. It seems to put the cart before the horse, to require observers in order to explain the universe that gave rise to observers. But Wheeler was gesturing towards something important, something that quantum mechanics genuinely does suggest, that at the most fundamental level, reality is not a collection of things with definite properties existing independently of all observation. Reality is a network of relationships, of interactions, of measurements, and the classical world of definite facts emerges from this quantum substrate to a process we do not yet fully understand. Let us consider the arrow of time once more, from a slightly different angle. The laws of physics, with one notable exception, are symmetric under time reversal. If you took a film of any physical process, an electron interacting with a photon, a proton decaying, two galaxies merging, and played it backwards, the reverse process would also be allowed by the laws of physics. And yet the world we observe is profoundly asymmetric in time. Eggs break but do not unbreak. Stars burn but do not unburn. Life ages but does not de-age. This asymmetry arises not from the fundamental laws, which are mostly time-symmetric, but from the initial conditions. The early universe was in a state of extraordinarily low entropy, and the second law tells us that entropy must increase, giving time its direction. But here is the puzzle. Why were the initial conditions of the universe so special? Why did the Big Bang produce a universe of low entropy rather than a universe already in its maximum entropy state? In a universe of maximum entropy, nothing interesting happens. There are no stars, no planets, no chemistry, no life. There is just a uniform lukewarm gas slowly spreading through an infinite space. The fact that we find ourselves in a universe of low entropy, a universe full of structure and complexity, and the dramatic processes of stellar evolution and galaxy formation and biological life, tells us that the Big Bang produced a very special initial state. special in a way that seems to demand explanation. Penrose has calculated that the probability of the Big Bang producing the universe we observe, chosen at random from all possible initial states of equivalent energy, is approximately 1 in 10 to the power of 10 to the power of 123. This number is so incomprehensibly small that the universe's observed initial conditions cannot be the result of chance. Something must have constrained them, some physical principle or law that we have not yet identified, something that ensured or strongly favored the low entropy beginning that gave rise to everything we see. This constraint is sometimes called the past hypothesis, the assumption that the universe began in a state of low entropy, and its origin is one of the deepest open questions in physics and cosmology. Some theorists argue that quantum gravity will eventually provide the answer, that a correct theory of the quantum beginning of the universe will automatically produce the low entropy initial conditions, that the wave function of the universe with appropriate boundary conditions selects for the smooth, ordered beginning we observe. Others argue that the entropic principle saves us again. Only in a low entropy universe can observers exist, so we should not be surprised to find ourselves in one. But this merely restates the question rather than answering it. We should spend some time with black holes, because black holes are intimately connected to the question of cosmic origins and may hold clues about what lies beyond the singularity. A black hole is a region of space-time where gravity is so intense that nothing, not light, not any signal, not any influence, can escape. At the center of every black hole, according to general relativity, lies a singularity, a point of infinite density and infinite curvature, similar in mathematical character to the singularity of the Big Bang, but reversed in time. A black hole singularity is in the future for anything that falls through the horizon. The Big Bang singularity was in the past of our universe. If quantum gravity resolves the singularity of the Big Bang, replaces the infinite density with a finite but very high density, a quantum gravity regime where the smooth classical spacetime breaks down into something more fundamental, it should also resolve the singularities inside black holes. In loop quantum gravity, models suggest that the singularity inside a black hole is replaced by a region of high but finite density, beyond which spacetime continues, potentially into a new region of spacetime. In some models, this new region has the character of a new expanding universe, what has been called a black hole bounce, analogous to the Big Bounce, where the collapsing matter inside a black hole reaches maximum density and then rebounds, creating a new space-time region that inflates outward on the other side of what was the singularity. This would mean that every black hole is, in some sense, a universe. That our universe was born from the collapse of matter inside a black hole in a parent universe. That the black holes forming in our universe are, right now, generating new baby universes, invisible to us behind our event horizons. This picture, sometimes called fecund universes or cosmological natural selection, was developed by Lee Smolin, who added to it an evolutionary twist. If the physical constants of each baby universe are slightly randomized relative to the parent universe, then universes that produce many black holes, because they have constants suitable for long-lived stars and gravitational collapse, will produce many offspring, and over cosmic generations, the population of universes will be dominated by those with constants that maximize black hole production. Our universe's constants, Smolin argues, are near the maximum for black hole production given the constraints of physics. This is a beautiful and audacious idea, applying the logic of natural selection to cosmology itself. It makes, in principle, testable predictions. If our constants are near the maximum for black hole production, then small changes to any constant should reduce the number of black holes our universe can form. Some physicists find this intriguing. Others are skeptical, both of the specific predictions and of the underlying mechanism. The transmittance of physical constants from parent to child universe is a conjecture without a detailed physical mechanism. But it is a conjecture that takes the form of a scientific hypothesis. It makes predictions that could, in principle, be tested, and that is a virtue. It is worth pausing to appreciate just how strange all of this is. We began with a question that seemed simple: what created the Big Bang? And we have arrived at visions of eternally inflating multiverses, universes that bounce, black holes that give birth to new cosmos, wave functions of the universe, imaginary time, mathematical structures existing without physical substrate, and the possibility that the question itself may be meaningless. The strangeness is not a failing of our theories. It is a reflection of the genuine strangeness of the universe at its foundations. Our everyday intuitions evolved to help us survive on the surface of a medium-sized planet orbiting a medium-sized star. They are beautifully calibrated for a world of rocks and rivers and predators and prey. They are not calibrated for the quantum gravity regime, for scales of space and time billions of orders of magnitude smaller than anything we encounter in daily life. And yet we are using those same minds, expanded and sharpened by mathematics and experiment and centuries of accumulated insight, to reason about the deepest nature of reality. That we have come as far as we have is extraordinary. That there is so much further to go is the gift. Dark energy deserves a moment of our attention in this context, because it is one of the most profound mysteries of contemporary cosmology and may be connected to the question of cosmic origins in ways we have not fully understood. In 1998, two independent teams of astronomers studying distant type Ia supernovae as standard candles to measure the expansion history of the universe made a discovery that shocked the physics community. The expansion of the universe is accelerating. Galaxies are not just moving away from each other. They are moving away from each other faster and faster. Something, dark energy, they called it, a placeholder name for our ignorance, is pushing space itself apart, overcoming the gravitational attraction of all the matter in the universe at the largest scales. Dark energy constitutes approximately 68% of the total energy content of the universe. It is, in terms of energy, the dominant component of the cosmos. And we do not know what it is. The simplest explanation is that it is the energy of empty space, the cosmological constant that Einstein introduced and then abandoned, the zero-point energy of quantum fields permeating all of space-time. But when physicists calculate the expected value of this vacuum energy from quantum field theory, they get a number approximately 120 orders of magnitude larger than the observed value of the cosmological constant. This is the worst prediction in the history of science, a discrepancy so enormous that it suggests something fundamental is missing from our understanding. The cosmological constant problem is, in some ways, a new version of the question we have been asking all along. Why is the energy of empty space the value it is, rather than the value quantum field theory naively predicts? Why is it small enough to allow galaxies and stars and planets to form, but large enough to drive the late-time acceleration of the universe? The anthropic argument suggests that we should not be surprised by this value. If it were larger, structure would not form, and we would not be here. But the multiverse of string theory's landscape, if it exists, does provide a vast collection of possible values, and in combination with the anthropic selection principle, it may explain why we find ourselves in a universe with a cosmological constant in the habitable range. The relationship between dark energy and the universe's ultimate fate also carries echoes of the creation question. If dark energy is truly a cosmological constant, a fixed property of empty space that does not change with time, then the universe's expansion will accelerate forever. Over trillions of years, The galaxies beyond our local group will recede beyond the cosmic horizon, invisible to any future astronomer. Stars will burn out, one by one, over hundreds of trillions of years. Black holes will evaporate through Hawking radiation over incomprehensibly long timescales. And the universe will approach its maximum entropy heat death, a cold, dark, uniform, structureless expanse of photons and a few relic particles, expanding forever toward infinite dilution. In Penrose's conformal cyclic cosmology, this heat death is not the end but the doorway to a new beginning. In the eternal inflation picture, our universe's heat death is irrelevant to the vast inflating multiverse, which continues to generate new bubbles long after our local pocket has grown cold and still. In loop quantum cosmology, the universe might bounce again, though the specific conditions for a bounce in a cosmological constant-dominated universe are not yet clear. And in Tegmark's mathematical universe, each history, each mathematical structure that exists, plays out completely, timelessly, including ours, in its full length from the quantum beginning to the heat death at the end. There is a word that comes to mind when contemplating all of this, a word that the great scientists and the great poets have reached for across the centuries when confronted with the enormity of existence. The word is awe. It is not a very scientific word. It does not appear in equations. It cannot be measured or quantified or submitted to peer review. And yet, it is perhaps the most honest response to what we find when we look at the universe at its most fundamental level. Awe at the fact that the universe exists at all. Awe at its mathematical elegance, at the deep and beautiful laws that govern its behavior from the quantum foam of the Planck scale to the large-scale structure of the cosmic whip. Awe at the fact that from a hot, dense, undifferentiated beginning, the universe evolved over 13.8 billion years into something that includes consciousness, includes beings who can wonder, who can ask questions, who can build telescopes and particle accelerators and mathematics, and use them to peer back toward the beginning of time. Carl Sagan spoke often of the cosmos as something deeply personal, something we are part of rather than observers of. We are, he said, a way for the cosmos to know itself. This is not merely poetic. It is physically precise. The matter that makes up our bodies was forged in stellar nucleosynthesis, scattered by supernovae, gathered by gravity, organized by chemistry, shaped by evolution, and assembled over billions of years and countless generations into beings capable of self-reflection. We are the universe in a very real sense, looking at itself. And when we ask where the universe came from, when we trace the history of space-time back toward the singularity and peer into the quantum fog of the very first moments, we are the universe asking about its own origin. This creates a strange loop, a kind of cosmic recursion. The universe created conditions for life. Life created conditions for intelligence. Intelligence created conditions for science. Science is now asking how the universe came to exist. The questioner and the question are the same entity, separated only by the extraordinary distance of scale and time. We are singularities of awareness embedded in a universe that may or may not have arisen from a singularity of density and temperature. We are, in a very profound sense, the universe's way of asking about itself, and the question we are asking is, why am I here? The honest answer, the answer that respects both the power of human knowledge and its limits, is this: we do not know. We have extraordinary ideas, beautiful theories, suggestive mathematics, and preliminary observations. We have the Hartle-Hawking no-boundary proposal, eternal inflation, loop quantum cosmology, conformal cyclic cosmology, the multiverse landscape, the mathematical universe hypothesis, quantum tunneling from nothing, and a dozen other frameworks, each capturing something important, each incomplete in its own way. We are at the beginning of understanding, not the end. We are, in the history of cosmic self-knowledge, in the equivalent of the early days of astronomy, when people first realized that the wandering stars were not gods, but bodies moving in space according to laws that could be written down and understood. The fact that we do not know is not a reason for despair or for invoking explanations that lie outside the domain of physical inquiry. It is a reason for continued investigation, for building better telescopes and more sensitive detectors and more powerful computers and more powerful mathematics. The history of science is a history of questions that seemed unanswerable, yielding, slowly and sometimes subtly, to persistent and creative inquiry. The nature of the stars, the structure of matter, the origin of species, the mechanism of heredity, the large-scale structure of the universe, each of these seemed, at some point in history, to be beyond the reach of human knowledge. Each yielded, in time, to the patient application of the scientific method. The origin of the universe may yield too. It may not. There may be aspects of this question, the deepest aspects, the question of why there is anything at all, that lie permanently beyond the reach of any empirical science, that reside in the domain of metaphysics or mathematics or philosophy or something we do not yet have a name for. But the boundary between the knowable and the unknowable is not fixed. Every generation has believed that certain questions were permanently beyond reach, and every generation has been proven partially wrong by the next. We should hold our confidence in the limits of human knowledge with appropriate humility. We should also acknowledge that the question we have been exploring, what created the Big Bang, is not merely academic. It is not just a puzzle for cosmologists and philosophers to argue about in seminars. It is the deepest possible expression of the human impulse to understand, the impulse that drives all of science and much of art and philosophy and religion. To ask where we came from, at the most fundamental level, is to ask who we are. It is to stand at the edge of the known and look into the dark beyond, not with fear, but with the peculiar, restless, insatiable curiosity that is perhaps the most defining characteristic of our species. There is a temptation, when facing a question of this magnitude, to retreat into the comfort of familiar frameworks, religious, philosophical, or scientific, and declare the question answered. But intellectual honesty requires that we resist this temptation. No existing framework fully answers the question of what created the Big Bang. Not the no-boundary proposal, which describes but does not fully explain the universe's quantum beginning. Not eternal inflation, which defers the question to the origin of the inflating background. Not the mathematical universe hypothesis, which reframes but does not eliminate the question of why mathematical structures exist. Not religion, which posits a creator and then faces the question of the creator's origin. Every answer at this level of depth gives birth to a new question, and the chain of new questions extends outward toward a horizon that recedes as we approach it. This recession of the horizon is not a failure of understanding. It is the nature of understanding itself at the edge of knowledge. The more we learn about the universe, the more we realize there is to learn. The more precisely we can describe the first moments of cosmic history, the more clearly we can see the questions that remain. This is not frustrating. It is glorious. It means that the universe is not small, not shallow, not exhausted by any finite investigation. It means that every answer is the beginning of a new adventure. The particle accelerators at CERN and elsewhere push our understanding of fundamental physics to energies of the order of tera-electron volts. The energies of the early universe, in the first tiny fractions of a second, reached energies of the order of 10 to the 19 giga-electron volts, the Planck energy, 16 orders of magnitude beyond what our most powerful accelerators can reach. We cannot recreate the conditions of the Big Bang in any laboratory we could realistically build. We must infer those conditions indirectly from the large-scale structure of the universe, from the cosmic microwave background, from the abundances of light elements synthesized in the first few minutes of cosmic history, from the theoretical frameworks that best fit all available data. This makes cosmology a uniquely challenging science. We cannot run the experiment multiple times. We have one universe to observe, one set of data, one cosmic history to reconstruct. We must be extraordinarily careful about confirmation bias, about the human tendency to see patterns in noise, about the temptation to believe beautiful theories without sufficient empirical support. The history of cosmology is full of beautiful theories that turn out to be wrong, or partially wrong, or right in unexpected ways. The steady-state theory, which held that the universe was eternal and unchanging, and that matter was continuously created to fill the voids left by expansion, was an elegant idea. It was wrong. The inflationary universe, introduced as an elegant solution to several cosmological puzzles, may be right. The evidence is suggestive, but not yet conclusive. Science advances through this interplay of beautiful ideas and brutal empirical testing. The brutality is not cruelty, it is necessity. Reality does not care about our theory's elegance. It cares only about what is true. And determining what is true about the very beginning of the universe is perhaps the hardest empirical challenge our species has ever faced. It is a challenge worthy of our best efforts, our most careful thinking, our most sensitive instruments, and our deepest humility. As we approach the closing of this exploration, it seems right to return to the question one more time, not in hopes of resolving it, but of holding it clearly. What created the Big Bang? The universe began 13.8 billion years ago in a state of extraordinary density and temperature, in the very early moments of which the physics we know breaks down. Before a certain moment, perhaps of the order of Planck time, we have no reliable physical description of what was happening. The universe may have tunneled into existence from nothing, in a quantum event with no prior cause. It may have bounced from a previous contracting phase, a predecessor universe whose contraction seeded our expansion. It may be one of infinitely many bubbles in an eternally inflating multiverse, a local end to inflation in an inflating background without beginning. It may be one aeon in Penrose's conformal cyclic sequence, the child of a previous universe's cold final state. It may be one mathematical structure among all possible mathematical structures that simply are timelessly in a platonic landscape of pure mathematics. Or, and this possibility must be held alongside the others, it may be something entirely different from any of these, something that no one has yet imagined, a framework so foreign to our current thinking that it will require a revolution in understanding comparable to the Copernican revolution, or the Darwinian revolution, or the quantum revolution. Such revolutions have happened before. They will happen again. The universe has surprised us before. It will surprise us again. What is certain, what the totality of human experience and human knowledge suggests with overwhelming force, is that the universe is real, that it is governed by comprehensible laws, and that the application of careful reasoning and empirical investigation to the question of its origin will yield, over time, insights that we cannot currently anticipate. The path from the burning question to the partial answer to the new and deeper question is the path of science, and it is a path of extraordinary beauty. We began, all those years ago in our collective history, by watching the stars and asking what they were. We have come so far. We have measured the composition of stars with spectroscopes, the distances to galaxies with the period luminosity relation of Cepheid variables. the age of the universe from the cosmic microwave background, the nature of space-time from the motion of binary pulsars, the existence of gravitational waves from the merger of black holes a billion light years away. We have set instruments into the outer solar system, listened to the radio murmur of distant quasars, mapped the large-scale structure of the cosmos in 3 dimensions across billions of light years. We have descended, in our imagination and our mathematics, to scales far smaller than any atom, to the Planck length where space and time themselves may cease to have meaning. We have ascended, in our telescopes and our theories, to scales far larger than any galaxy, to the topology of the universe as a whole. And through all of this, through every discovery and every revolution and every humbling correction, the fundamental question remains, still open, still vibrating with all the force of its original asking. What came before? What was the seed of everything? What is the ground of being? Why is there something rather than nothing? These are not questions that will be answered in a single paper, a single discovery, a single generation of scientists. They are questions that will accompany us into the future, growing richer and more precisely formulated as our knowledge grows, leading us always forward into deeper understanding and deeper mystery. There is a peace in this, if we allow ourselves to feel it. A peace in the recognition that the universe is larger than our ability to comprehend it, and that this largesse is not a reproach but an invitation. We are small by cosmic measures. We are brief by cosmic timescales. Our planet is a pale blue dot in the outer arm of an ordinary spiral galaxy in a universe of 2 trillion galaxies. And yet here we are, asking the deepest questions. Here we are, building instruments of extraordinary sensitivity to hear the faint echoes of the universe's birth. Here we are, writing equations that describe the curvature of space-time and the quantum properties of matter and the large-scale topology of the cosmos. This is remarkable. It is the most remarkable thing about the universe, not its size, not its age, not its complexity, but the fact that it has produced, in at least one small corner of one ordinary galaxy, beings capable of wonder. Beings who ask not only how to survive, but how the universe began. Beings who look at the night sky and see not just darkness and distant fire, but depth and history and question. The question remains, what created the Big Bang? We do not know. And in not knowing, we are most ourselves, curious, humble, reaching, alive to the mystery of a universe that gave rise to us, and that we are only beginning to understand. The cosmos is not finished with its surprises, and we are not finished with our questions. The two facts together, the universe's inexhaustibility and our undying curiosity, are perhaps the most beautiful thing in all of existence. They are the guarantee that the conversation between mind and cosmos, this strange and magnificent conversation that began when the first human looked at the stars and wondered, will continue for as long as there are minds to ask and stars to answer. In the end, perhaps, the question is its own reward. Not because ignorance is acceptable, not because the search for knowledge is futile, but because the question of what created the Big Bang, the question of ultimate origins, of why existence exists, is the question that drives the deepest and most beautiful and most human of all enterprises, the attempt to understand where we came from and what we are. It is the question that has no final answer, or whose final answer is always the beginning of a deeper question. And perhaps that is exactly as it should be. Perhaps the universe is not a closed book waiting to be read, but an open conversation, an ongoing dialogue between the cosmos and the minds it has produced. A conversation that began with the first flash of cosmic fire 13.8 billion years ago and continues in this very moment, in the mind that holds this question, in the silence that follows every answer and gives birth to the next question. We are here. The universe is here. The question is here. And that is enough to sustain a species, and a civilization, and a science, for as long as the stars continue to burn.